Welcome. In the last class we saw a quantity called the partial molar property. We said that it is a conceptual quantity which we had defined so that we could estimate the total property as just a weighted sum made with the mole fractions of this conceptual property. Now in this class let us look at one of the ways of estimating partial molar properties from experimental data. The data that we need is from mixing experiments. You mix 1 and 2 and 3 whatever, and then you initially measure the property of the pure component, and then you measure the property of the mixture very carefully of course, and this is the kind of data that we need to estimate the partial molar properties. The typical variables that are measured are volume and enthalpy, but the method is applicable to any extensive property. And since volume has an intuitive feel to it, we know that volume means something, it is the amount of space that it occupies. We will use that to demonstrate the partial molar property. Enthalpy might be a little more difficult to imagine, and therefore we will use volume, and then you can kind of extrapolate that to all other extensive properties. Usually there is a change in volume when mixing of two components occurs. That is the reason why we are doing this. We will limit ourselves to a binary system. The final volume of the mixture is going to be different from the sum of the volumes of the pure components before mixing. And let us say that in this binary system V1 and V2 are the molar volumes of the two pure components 1 and 2, and let us say that V1 T hash and V2 T hash be the partial molar properties in a solution containing N1 moles of component 1 and N2 moles of component 2. The difference in volume upon mixing is quite easy to see. Let us represent that as delta of Vt, the total difference in volume upon mixing. This is the volume after mixing minus the volume before mixing. The volume after mixing we said can be obtained by the weighted sum of the individual volumes, and that is where we brought in the partial molar quantities. Therefore the volume after mixing is N1 V1 T hash plus N2 V2 T hash minus the volume before mixing is for each pure component N1 moles of the pure component 1, therefore N1 times the molar volume of 1 V1 gives you the volume of 1, and N2 times V2 gives you the molar volume of the second component. Therefore this minus this is quite obviously the difference in volume upon mixing. If we recombine the terms by taking N1 common out, N1 into V1 T hash minus V1 as here plus N2 into V2 T hash minus V2. We will call this equation 419. If we divide equation 419 throughout by N1 plus N2, the volume change per mole of the solution can be written down, and therefore delta V of T becomes just delta V. This is the molar volume of change. This is nothing but N1 by N1 plus N2 becomes X1. Since it is a binary solution, X1 plus X2 will be 1, and therefore X1 can be written as 1 minus X2. Therefore 1 minus X2 into V1 T hash minus V1 plus x2 times N2 by N1 plus N2 is x2 times V2 T hash minus V2. Let us call this equation 420. X2 of course was the mole fraction of component 2 in the binary solution, that was quite clear. If we plot the experimental data on volume changes from mixing experiments as a function of x2, the volume change in the y axis and the mole fraction on the x axis, we will get a curve something like this. This is delta V, the molar volume change upon mixing as a function of the mole fraction of the component 2 varies between 0 and 1. We get a curve A G B. This is the variation in the volume upon mixing. Take a look at this figure. C G D is the slope of this curve A G B at the point G, it is quite evident here, and also these are distances which I have indicated by dotted lines G F, F E, C F, C A and so on. What I would like you to do is juggle your brains around a little bit and try to figure out how we can use this figure to get at the partial molar property, let us say V1 hash or V1 hash. Why don't you think about it, do it, take about 15 to 20 minutes to do it, there is no hurry, but this is the basis here. I would like you to think about it. It comes from the definition of the slope, which is essentially the slope, the derivative here, derivative at this point, and then relating it to the distances here. So take about 15 to 20 minutes to come up with that, and then I will give you solution step by step. Go ahead please. Let me start working this out for you and give you some hints and help you get to the solution. As we had seen, this is nothing but delta V versus x2. This is the curve AGB that we will get, the variation in molar volume change upon mixing as a function of x2. The slope of the curve AGB at a particular point E on the x axis, this particular point E, at this point what would be the slope here is nothing but the derivative. If you differentiate equation 418, here, let us not go too far behind, it is quite easy to see this. You have a curve, you have delta V as a function of x2, which you got from here itself. You can start with this itself, 420 itself, and if you differentiate that, assuming constancy of pressure and temperature, if you use equation 420 differentiated by the chain rule, dou delta V dou x2 at the point E, here somewhere here, we are doing this differentiation at the point E and we are doing the differentiation of this equation. So, dou delta V dou x2 at the point E, okay. Please keep this in mind when you are differentiating it, is nothing but 1 minus x2 again by chain rule, 1 minus x2 dou V1 t hash dou x2 minus V1 t hash minus V1, taking 1 minus x2 into this, therefore first function into derivative of the second function, which will turn out to be d1 t hash dx2 minus the second function to derivative of the first function d dou x2 will turn out to be 1. Therefore, that is the first term, plus the second term is x2 dou V2 t hash dou x2 plus V2 t hash minus V2, both taken at the point E, and since x1 equals 1 minus x2 in a binary system, we have already seen from equation 1.8 sum over xi dmit hash equals 0, and therefore, what do you get? Okay. This using this, what can you how can you simplify whatever derivative that we had written previously here? This is the derivative we have here, and this is the hint that I am giving you for the next step, summation of xi dmit hash equals 0. So, how can you simplify the previous equation? Go ahead, take the next 5 minutes, 5 to 10 minutes if you want, and do it. Go ahead, please. Okay, if we apply this summation of xi dmit equals 0, what is this? This is nothing but x1 in our current binary case, x1 dm1 t hash plus x2 dm2 t hash equals 0, or 1 minus x2, x1 can be replaced as 1 minus x2, 1 minus x2 d1 t hash dou d1 t hash dou x2 plus x2 dou v2 t hash dou x2, this equals 0. And where does this happen? It happens in the previous equation here. This, the combination of this and this can be set to 0, and therefore dou x2 of delta V at E just happens to be these two terms. There is a minus here. So, let us write this first, V2 t minus V2, V2 t hash minus V2 set at E minus of V1 t hash minus V1 at E, and that is what this one says. Therefore, dou x2 of delta V at E equals, okay, we have taken the minus here first, does not matter, minus of V1 t hash minus V1 at E plus V2 t hash minus V2 at E. It is okay. Equation 422. Now, can you take another 5 minutes to see how you can interpret these in terms of the distances given in the figure. The figure 4.1 that I had shown, the AGB curve delta V versus x2, see how these quantities can be related to the distances given in the figure. Take another 5 minutes. This is a geometric interpretation of that, and that gives us the basis for estimating the partial molar properties. You would have probably figured out what these mean in terms of the distances. Now let me tell you what it is, just check whether you got it right. Before we do that, let us eliminate to do that effectively. Let us eliminate V2 T bar minus V2 at point E between equations 420 and 422. What is 420? This 422 is this, we have a V2 T bar minus V2 at E, and 420 was this x2 into V2 T bar minus V2, this one exists here. Therefore, let us use these expressions to write V2 T bar minus V2 in terms of the other variables here. If we do that, we will get, please do this and check, delta VE equals 1 minus x2 at E into V1 T bar minus V1 at the point E, V1 T hash minus V1 at the point E, plus x2 at the point E into V2 T hash minus V2 at the point E. Therefore, V2 T hash minus V2 at the point E, which we are trying to eliminate, we had used equation 420 to eliminate this. We could write this in terms of the other variables by transposing delta VE minus, take this to the other side, 1 minus x2 at E, V1 T hash minus V1 at E, and there is an x2 factor here, therefore divided by x2 E. And from equation 422 at the point E, the equation 422 was this by transposing we can write this in terms of the derivative and this particular quantity. V2 T hash minus V2 at E equals dou x2 of delta V at E plus V1 T hash minus V1 at E. And since the left hand sides are equal between the previous equation and this equation, we can equate the right hand sides, and therefore dou x2 of delta V at E plus V1 T hash minus V1 at E equals the right hand side on the previous equation, delta VE minus 1 minus x2 E into V1 T hash minus V1 at E divided by x2 E. Therefore, if we transpose this equation, cross multiply, and you know how to do this, you can cross multiply and get, essentially we are looking at getting some way of finding out V1 T hash. If you do the algebra, you would get this as the first step, multiply, cross multiply by x2 E into dou x2 of delta V at E plus x2 E into V1 T hash minus V1 at E equals delta V E minus 1 minus x2 at E V1 T hash minus V1 at E, and transposition getting V1 T hash minus V1 terms together, we could group them as V1 T hash minus V1 at E common take out times x2 E plus 1 minus x2 E equals delta VE minus of x2 into dou x2 of delta V at the point E. Therefore, V1 T minus V1 at the point E equals delta VE minus x2 E into dou x2 of delta V at the point E. And what does this represent on the graph was the earlier question, and this what does this represent and what does this represent? You know, the derivative is the slope of the line or the tangent of the angle made at a particular point in this graph. You know, we are trying to get delta VE. What is delta VE? Delta, the value of delta V at the point E, which happens to be the distance GE. Therefore, this can be replaced by this distance GE. X2 E is nothing but AE or CF, you know, this distance, and dou delta V dou x2 at the point E is nothing but the slope of the tangent, that is the definition of the derivative itself from your calculus class, which is nothing but the tan of the angle that this line makes with the horizontal line here. What is tan? Opposite side by adjacent side, GF by CF, and therefore EG minus AE x2 times GF by CF. That is what this is. This is the geometrical interpretation of this particular quantity, which can of course be written as EG minus GF Why? Because AE and CF are the same quantities, therefore you can cancel AE and CF here. Therefore, EG minus GF, which is nothing but AC, which is nothing but the intercept of the tangent made at the point G on the y axis. Therefore, the intercept of the slope with the x2 equals 0 line, which is the y axis, gives us V1 T minus V1 at the point E. V1 of course is the molar volume of the pure component, that is easily known, and once you know the intercept, you could get V1 T hash. That is what is given here from the intercept value, and V1 the partial molar volume, V1 T hash can be estimated. Now, a similar geometric interpretation gives V2 T hash minus V2 E equals the other intercept. What I would like you to do is to convince yourself that it is indeed the other intercept. Convince yourself by going through the same procedure again. I would like to leave that as homework for you, and when we begin the next class, we will take things further.